organisation that develops and the exchange of engineer knowledge within the power system industry. The community features 60 national committees spanning 90 plus countries, 15,000 members and growing, and 1,250 member organisations. The NGN as an organisation which is specifically allows young professionals to develop their knowledge in the power system industry through such things as site visits, industry-related events, valuable networking opportunities, to be involved in CIGRE working groups and technical events, and provides a platform where early career professionals can feel comfortable sharing their ideas and get an opportunity to interact with industry experts. Before we start, a bit of background on our presenters. Rohit Trivedi is a research assistant at the IERC working on projects relating to microgrid operation and control and local energy market framework. Prior to that, Rohit was working on quantum machine learning project dedicated to the healthcare system at the University of Bradford, followed by power system software engineering internship at TNAI Services in Manchester. He is also a representative of CIGRE Working Group C145 and volunteers for the IET at a Young Professional Ambassador. Valentin received a bachelor's engineering degree from UNC in Argentina and a master's degree from Politecnico de Torino in Italy in 2014. He has also received a PhD from UCD in Ireland in 2020. He's a senior energy systems researcher at UCD Energy Institute. His research interests include distribution systems, planning and operation, smart grids, and distributed energy resource and integration. Finally, presenter 3 is Valerie Lynch. She's a data science manager for ESB. She leads a team responsible for delivering business insights through interpretation of large data sets from across the business. Valerie has over 15 years experience in the utilities industry, and the presentation will focus on the use of machine learning to segment customers in arrears and how machine learning can support the business to make informed decisions with this type of analysis. So now, without further ado, I'll hand you over to Rohit for his first presentation. It might take a minute there, Rohit, to get over to you.
Keith, I think that the stream is not on.
It's not on?
I don't think so. No, because there was a problem with the YouTube link.
Okay.
Yeah, so I don't know if Camille is here. So what I would say is that Camille can create a new link. We send it by email to the people. We share the link on Slido. We can maybe postpone the start to 14:30. We'll have to cut things so we don't end up later than we had in mind, and then try to get everything ready in 15 minutes and we start again 2:30.
Yeah, it's probably a good idea.
Yeah, I think that's the best option. Sorry to all, we've had some issues, and we will send out the new YouTube link. So we might go.
We'll probably just go straight to the 3 presentations in the question Q&A, will we?
Yeah,
exactly. Yeah.
Great.
So we'll be circulating the new link to everyone who registered to the event. We'll be circulating the new link in the next few minutes, and we will go back onto the new link at half 2, so we can look at the presenters' presentations. So sorry again for the inconvenience.
Connor, I have WhatsApp open here, so I can share the link to the Slido. Do you want me to do that?
Yeah, that might be a good idea.
Make sure that that's the proper link, that we are not going to be like getting a new one or.
Yeah. I'll just.
You say it's top 2.
That link, I clicked on it there. It says it's streamed for 7 minutes.
Okay, Camila, are you here? Oh yeah. So what is the issue? Okay. Okay. And now you created a new event with a new link. Is that one working? You can pre-check if you go to YouTube on your YouTube studio, you see that you get kind of like a pre-visualization on the top left of the video. You can unmute that one and you will be able to hear from your computer if there's audio coming through.
Presume Connor will go back from the start again anyway.
Yeah, I think that might be the best because I had to apologise. I don't think the audio was working from the start. So
yeah, no worries.
Yeah, so we might have to start again, everyone. So
it's great practice for me.
That's it. Fire away there, Keith.
Ready to go, yeah. Good afternoon, everyone. You're all very welcome to our first event of Q2 2021 for the CIGRE Ireland Engineering Group. This event will be on the application of machine learning techniques in the power system industry. My name is Keith Keedy and I'm the Vice Chairperson of the Engineering Group, and I will be the event chair as well for this afternoon's event. I am delighted actually to be joined by three excellent industry guests who will give a presentation each on machine learning and the role it has to play in our industry. Dave Fint, I'm not sure, is this coming across, Connor?
Let me know when you're there.
I believe
I'll just go through the event agenda anyway.
On its way, folks. So the event will be back up and running now in a few minutes. Sorry again about the delay.
I presume we'll just start with Rohit's presentation, Connor, will we?
Yeah, I think that's best
yeah,
off.
Maybe you can do like a 1-2 minutes.
Back up and running now in a few minutes.
Yeah,
because like people didn't even hear the first one, so you won't.
I presume we'll just start with Rohit's presentation, Connor, will we?
Yeah,
so, anyway, Camille, did you manage to check on that?
Yeah,
because like people didn't even hear the first one, so you won't.
I presume we'll just start with Rohit's presentation, Connor, will we?
Yeah,
so, anyway, Camille, did you manage to check on that?
Yeah,
because like people didn't even hear the first one, so you won't.
I presume we'll just start with Rohit's presentation, Connor.
No, but you should be able to check if you just. So you have on the YouTube thing where you can click on start stream on the web, and then you should have like a little. Okay.
Keith, can I take control of the laser pointer? I was not able to see that.
I'm not sure how do you go about that, Rohit?
If you give me control, I would like to see if I can control.
Yeah, it's going to you there now.
I cannot see the.
Oh, you have, yeah, click, yeah, there you
go. Okay. Yeah, it takes time. Okay, that's fine. Thank you.
No problem. Should we start?
I think we're good to go, Keith.
I'll just kind of go quick through it. Good afternoon, everyone. Apologies, we had technical difficulties a few minutes ago, but you're all very welcome to our first event of Q2 2021 for the CIGRE Ireland NGN. This event will be on the application of machine learning techniques in the power system industry. My name is Keith Keady, and I'm the Vice Chairperson of the NGN Group, and I'll be the event chair for this afternoon's event. I'm delighted to be joined by three excellent industry guests who will give a presentation on machine learning and the role it has to play in our industry. So just the event agenda, there's going to be three presentations from Rohit Trivedi, Valentine Rigione, and Valerie Lynch on machine learning topics. For questions, you can use the Slido. It should be on the right-hand side of your stream. It should be hashtag CIGRE 2021. We'll be taking all questions at the Q&A session at the end of the three presentations. But you can log your questions throughout the presentations, and we'll take them at the end of the conclusion of the three presentations. I'll be joined at that point by Katie Hurley, who will be asking the questions of the presenters. Before we begin, just a brief update, brief information on CIGRE as an organisation for anyone who doesn't know or isn't familiar with the organisation. CIGRE is a worldwide organisation that develops and exchanges engineer knowledge within the power system industry. The community features 60 national committees spanning over 90 countries, 15,000 members and growing, and 1,250 member organisations. The NGN Group itself is an organisation that specifically allows young professionals to develop their knowledge in the power system industry through, say, site visits, industry-related events, valuable networking opportunities, to be part of CIGRE working groups and technical events. And it also provides a platform for early career professionals to feel comfortable sharing their ideas, to get an opportunity to interact with industry experts. Before we start, we'll just give a quick run through of the presenters, their background. Rohit is a research assistant at the IERC working on projects relating to microgrid operation and control in local energy market framework. Prior to that, Rohit has worked on quantum machine learning project dedicated to healthcare systems at the University of Bradford, followed by a power system software engineering internship at TNI Services in Manchester. He is also a representative of CIGRE Working Group C145 and volunteers for the IET as a young professional ambassador. Presenter 2 is Valentine Rigione. He has received a bachelor's engineering degree from UNC in Argentina and a master's degree from Politecnico di Torino in Italy in 2014. He's also received a PhD degree from UCD in 2020. He's a senior energy systems researcher at UCD Energy Institute. His research interests include distribution systems, planning and operation, smart grids, and distributed energy resource integration. Finally, presenter 3 is Valerie Lynch. She's a data science manager for ESB. She leads a team responsible for delivering business insights through interpretation of large data sets from across the business. Valerie has over 15 years experience in the utilities industry, and the presentation will focus on the use of machine learning to segment customers in arrears and how machine learning can support the business to make informed decisions with this type of analysis. So without further ado, I'll pass over control to Rohit and he can go through his presentation. It should come up there in 2 seconds now, Rohit.
Yeah, thanks, Keith, for the introduction. Welcome all. Can you hear me clearly?
I can hear you anyway.
Yeah, thanks. So yeah, welcome all. So I'll be discussing on managing peak demand with the battery storage system with the machine learning approaches. Going to the first slide. For the presentation, I'll be discussing why we need the battery storage. I'll be discussing the ML approaches with the case study that I have considered with a brief background, and then I will do some data analytics, some ML models that I've developed, forecasted, and then optimization of battery for managing the peak demand. And at the end, I'll be discussing where this overall technology can be used in the distribution network. So this is the first slide where it's very famous curve from Californian ISO. You can see, so this is a demand curve. The demand is very low during the daytime as compared to the rest of the day, where there is potential capability of generation more than the demand, because demand is very low during this period. And in the evening, as we go from 4 p.m. until 6 and 7 and 8, the demand is increasing rapidly, and this is where we need fast-acting dispatchable generators that can cope up with the increased demand. So as we are going to more renewable energy resources based power system, we need the storage devices and other generators that can be dispatched quickly. And overall, how we can manage the demand, and we can reduce this peak curve with the storage devices. So battery, I've taken battery as a storage system because it's easy for a plug and play kind of solution at all levels of the power system. So this is the case study that I will be discussing throughout the presentation. So here you can see there are PV and demand data has been taken from the substation in UK, which is in Plymouth. And the other 6 points are weather grid points where temperature and irradiation data has been taken. 2 weather grid points are in the English Channel, and the other 4 are on the territory of Britain. The total PV capacity is 5 megawatt, battery capacity is 6 megawatt hour. There are some constraints on the battery, like charging rate and maximum discharging rate of 2.5 megawatt every half an hour. And the discharging time is already fixed from 3:30 in the afternoon until 9 in the evening. This is a bigger stretch for, there is no general peak demand during 9 p.m., but for simplicity, this has been taken as a simple case scenario. So overall objective is to flatten the peak demand curve, and we will see how machine learning can be used here. Yeah, so this is the brief data analytics, where we see on the upper left corner, you can see the PV power output from 2018 to 2019 and 2020. So this is a 2-year data. The PV variation is almost the same during summer, and the pattern is same during the winter. And the right-hand side, you can see the demand. There are some outliers in the demand, but the data was almost very clean, so that we don't have to struggle with managing the data. There are many data analytics techniques to deal with the data and to see what are the patterns and trends in the data. But for simplification and presentation purpose, I use the correlation, that how our target variable, which is PV power, which will be forecasting PV and demand both. So how our target variable is related with the weather parameters. So the weather parameters include temperature at all the 6 locations you can see on the x-axis here, and the irradiation at all the 6 locations. So if you see the relation between these parameters with respect to the PV power, the temperature is not highly correlated, and the irradiation is highly correlated with the PV power. So if the value is less than 0.5, then we can neglect these parameters which are not correlated. But for irradiation, you can see the value is around 0.85, 0.86. So this is also a kind of technique where we extract the features from the data. So a kind of feature extraction technique in the machine learning algorithm. So we'll be using this irradiation data as features for predicting our PV power through machine learning algorithms. And in the demand side, you can see there is almost no correlation between these parameters, because all the values are near to 0. So demand has been considered as a univariate forecasting. So we have not considered any external parameter for forecasting demand. So we'll be using machine learning to predict the PV power and the demand, and how we'll manage the peak demand during the evening time. To reduce the training time, because for the machine learning algorithms, we have problem with longer training time. which is not feasible every time, especially if we are going through real-time solutions. So this is the seasonal demand pattern of 2018-2019 for all the seasons: spring, summer, autumn, and winter. So you can see the weekly demand pattern. Yeah, it's very random. There are no patterns in the demand. So we have categorized the data into seasons, and then we have individually forecasted PV power and demand both for these particular seasons. For the forecasting model, I've used the classical statistical model called ALIMA. And for neural network models, we have worked on CNN, LSTM, some RNN. And these are the two methods that we have developed for better forecasting. At this moment, I cannot give more insight on these two methods because the work is under publication. And until it is published, I cannot reveal the what we have done in these two methods. But yeah, we'll see how accurate these methods are. All these models have been evaluated based on the RMSE and normalized RMSE. There are many other metrics as well for detecting errors, but for this presentation and simplification, I've just used two root mean square error and the normalized root mean square, which is quite benchmark error comparison method. With all the forecasting models that we have analyzed here, as you can see, the M1 and M2 have outperformed all the existing methods. Yeah, I have also worked on other models, but I've not shown here because of the space and time limitation. Except these two seasons, spring 2018 and summer 2019, the M2 method was giving the least forecasting error. The normalized RMSE value was very less than 0.1. And for demand, M1 method has outperformed all the other methods. There is kind of explainability why M1 is better here, why M2 is better here, because the way we have developed the algorithm is quietly understandable. And yeah, later on, once the work is published, you can clearly see why these methods are giving accurate results. Yeah, so we have also worked on reducing the training time. So for PV forecast, here it should be M2, sorry. So M2 and M1, here the model trains from the data within 10 to 40 seconds, and so for the demand for 10 to 1/3 of a minute. So the models are very accurate, as well as we are not compromising the training time. So it is very scalable and can be used for the real-time control. When these results are chosen for the optimization of batteries, so this is a simple basic diagram where PV and battery storage are being connected with the distribution network, and here's the load demand. So what we are doing is the load demand is completely fulfilled by the PV and battery. We are not taking power from the distribution network unless necessary. In case PV is not available, then there could be some chances that there will be power flow from distribution network to the load. But in our case, for this presentation, I've taken this forecasted data. You can see this is the PV generation forecasted from, I think it was in summer 2019, for the 2 days of summer 2019. And I have not shown the results of all the models because the graphs was very messy. To give a clear insight and clear explanation, these are the 2 days in summer 2019 where the PV has been forecasted. And in the blue line below graph, you can see this is the demand, these are the peaks and valleys of a normal network demand without battery storage. But when the battery storage was installed, the demand, you can see the spike in demand, but this is the time where battery is charging and it is charging totally from PV. So this is not an additional burden on the network. And during the evening time when the forecasted results were sent to the optimization engine, it gives the almost flat demand because the overall this demand has been reduced, and the optimizer is automatically reducing this part of the demand and making the overall demand very flat from the network point of view. So this is how battery is charging and discharging. The battery operation, you can see we have compared with the actual data how it should have performed, how it has performed with the best model and with the baseline model, that is simply RNN model. So this is the battery operation. During the morning time, it is taking power from the PV directly, and during the evening time, it is discharging. So this is an area curve. You can see the best model is almost near to the actual model, and the error is almost 14% less than the baseline model. So this overall work is quite significant in terms of providing the real-time services to the grid, whether it is a grid services or any other services from the storage devices. Machine learning here is used for better forecasting and giving more accurate results over the existing conventional methods that are being used in the industry. And this is the final framework where the overall system can be integrated. You can see in the middle, there are 3 levels: TSO level, aggregator level, and prosumer level. So once we have better forecasting, and forecasting is obviously the extreme need for smart grid operations. And once we have more accurate results, we have the better preparedness of what's going to happen tomorrow. And especially in the control room of system operator, you can see during the peak demand, we have to make our generators completely on, spinning all the time, so that in case of any contingency, we can provide additional support from the storage services. So in this way, there are two things. First is the forecasting with ML models, and sending the results directly to the optimization engine, so that there could be an autonomous control of assets that can directly support the grid services in case of any contingency and whatever we have developed the algorithm for. Forecasting is obviously important, and further, it depends the level of control that will be required at DSO and aggregator and prosumer level, maybe centralized, decentralized, or maybe a distributed control. But there are challenges with this model that once the model is developed, then to make it more scalable, we will need more control operation, proper control algorithms, proper communication infrastructure. And moreover, if the prosumers want to participate in the energy market, and in Ireland, energy market is at the distribution level is very limited, and even if it is there, it's mostly fixed price basis. And to make it more competitive, if the wholesale market that comes into the distribution level, then the real challenge will start, and these forecasting models will be really useful for the distribution network and the energy market at the distribution level. So this was the overall work from me. From my side, if for any queries, you can always reach me at this email address. And thank you. Thank you for listening. Over to you, Kate.
Thank you, Rohit, for an excellent presentation. I will think I have there now. Turn off the razor. Right, for next presentation will be from Valentine. Val, I've sent you rights there to go on the screen.
Let me check. Yes, it works. So thanks, Keith. Hi, everyone. So yeah, my name is Valentin. I work as a researcher in UCD Energy Institute. And as Keith was mentioning before, well, most of my work is in the integration of distributed energy resources in distribution systems, particularly residential low voltage grids. That's an interesting topic because we all want to have more of these distributed resources, such as like electric vehicles and domestic scale photovoltaics, PVs, batteries, electric heat pumps, etc. But the problem is that all those networks, when they were designed, they were not done in such in a way that they had in mind that these technologies would be there. That means that now you have embed generation in the low voltage network. So what that means that customers are not really passive anymore. You have extra demand that you didn't have in mind before. So that means that you can start having congestion and voltage problems. So the idea is to come up with like cost-effective solutions for utilities such that they can integrate this technology in a secure way, but having in mind that those solutions need to be cost-effective, they need to be implementable in real time. That means that if you can have a super fancy algorithm to define when an electric vehicle should be charging, but if the algorithm is taking 9 hours to define what the electric vehicle needs to be doing in the next minute, it doesn't work. And at the same time, we need to have in mind that there's very limited communication and monitoring resources in the low voltage distribution level, practically none. So it's not that we can come up with the solutions that we have for the transmission system and just move them to the low voltage grid. So what I try to do is, well, the focus that we have in our lab is basically trying to move from passive network operation to active network management scheme for distribution utilities, and trying to move from centralized solutions, which is what you have typically in transmission system, to more autonomous or decentralized approaches. And what I'm going to show you today is 3 different pieces of research where we use machine learning as a tool in order to achieve that. So the first one was when we started working on this, well, we wanted to have observability of the grid. That means that, let's say that we have a distribution feeder and we have PVs there. Well, can we know what is the magnitude of the voltages, for instance, on the grid, so we can take actions if we see that those voltages are over what the grid code says. And the problem is that there is no communication right now between the different customers in the grid. There's no way of to have a centralized control that knows the measurements everywhere and applies like a traditional state estimation. So we said, well, what if we create a model of the grid knowing the impedances of the conductors and the topology and the customers that have PV, etc. And we do some offline process where what we do is start running a lot of power flow solutions where we start changing the operational set points of the PVs, so how much active and reactive power they are injecting or consuming, and see how the different variables respond. So for instance, how the voltages in a phase at a certain node going to change if we change the PV power injections, what the losses are going to be doing, what the currents are going to be doing, etc. And grabbing that information, we apply regression analysis, which is that machine learning, and we obtain a surface or a polynomial that would express, well, this is how your voltage in that point going to be affected by what the PVs are doing. And then we started exploring as well how these surfaces would be affected by changes on the demand on the system, changes on the voltage at the distribution transformer level because of the operation of the medium voltage grid, etc. And we found that there was a way of correlating all these surfaces to local measurements at every point of the grid. So basically, we created a method where if you have access at a PV location to the local voltage and the local power injection from your PV inverter, you can use the regression model in order to obtain a surface here that characterizes how the network is in its current state. So that means that if you know what your PV is doing and you know the local voltage, then you can get this surface, and by a direct calculation, you can then know, well, this is my estimation of what the voltage at the farthest node is going to be, or what the losses on the system are right now. And at the same time, well, the idea is that you can then take actions accordingly. So in terms of estimation, what I mean is that, for example, from this customer here, you could perform an estimation of what is the voltage over there, and then identify that at certain points there is a voltage violation because there's generation is too high and demand is low. And you can take actions because would be a voltage, no? And that voltage, basically you get that surface which is telling you that voltage is a simple expression of what the PVs are doing, basically how much active and reactive power the PVs are injecting. So then you can modify either active or reactive power from the PV according to whatever the characteristics of the inverter are, and then bring that voltage back to safe operation. And at the same time, you could also minimize losses on the system or minimize currents or minimize the reactive power flow exchange with the upstream network, curtailment, whatever you want, because all those variables, you can characterize them with these surfaces. And at the end of the day, well, get an operation of the grid where your voltages following some efficient effective function, are maintained within the limits that are defined by the grid code. No? So that would be one of the things that we did on state estimation. But then, I mean, there are different ways as well of integrating. In this case, would be PVs as well, without necessarily estimating the magnitude of the voltages and currents on the grid. And one of the most common practical solutions is the use of inverter functions. For those that are not familiarized with them, it's a simple either linear or quadratic or piecewise linear function that says you give it to the inverter of a PV and you say, well, if the local voltage is this value, then you should be consuming this amount of reactive power in order to compensate for the voltage rise caused by the active power generation of the PV. So if the inverter sees that the voltage is going up, it consumes more reactive power, or it makes that the power factor is smaller. And if it sees that the voltage is not as high, then well, the power factor can be closer to 1. No. The problem with this is that how do you define the values of those functions? Because once you have them, it's super simple. You go to the inverter, you put it to work, you don't need any telemetry system. There are two ways that people are calculating them. In academia, the most typical thing is that, similar to what I was showing you before, you get a model for your circuit, your low voltage circuit, and then you run a lot of simulations or optimizations in different situations for the demand and operation. And then you get, well, this is the parameters for that function that are going to work in all situations and are going to be super efficient. The problem with that is that first you need to have a lot of comprehensive information because you need to have a network model for all your low voltage circuits, which can be on the order of millions. That means that you need a lot of engineering resources and time to do the analysis. And at the same time, the other problem is that, well, what happens if the characteristic of the grid change? So you run all this extensive analysis and you had in a feeder with 40 houses, 10 of them had PV, but now it happens that 20 more households have PV. So now you have 30 PV. And well, your functions are not as efficient anymore because they were not calculated for the same grid as now. The other approach then that is proposed mainly by standards like IEEE, EPRI, and different utilities that, well, based on some information that we know and common experience, let's just define some standard function that you just use this regardless of which grid you are operating on. That's very practical for utilities because it's going to be better than not using anything or just coming out with parameters with no logic. But the problem is that they think that that solution is going to work for any network, regardless of what the characteristic of the network is. The problem with the LV system is that you can have a transformer and you can have a feeder that has 20 customers, and next to it, a feeder that has 150 customers. And they're totally different in terms of topology. So you cannot expect the same standard function to work in both cases. So what we proposed was something on the middle. So let's say, well, let's assume that you're a utility. Let's assume that you have models for your low voltage circuits for an area that is kind of like representative of your distribution system. And let's run some extensive analysis there and get these optimal inverter functions, okay? And based on the learning that you make from there, well, apply that learning in a new case for a new circuit that you don't want to perform this extensive analysis. So the way we did that is we use neural networks. So the idea here is that you create a training data set where you run that extensive, complex analysis to find optimal inverter functions. And then you also get some characterization features for the grids that you're using as test cases. So for instance, how many customers do the grid have? How many PVs were there? How many what was the percentage of customers with PV? What was the extension of the feeder? We were trying to not to keep try to leave aside parameters, kind of like impedance of the conductors. So trying to keep as low as possible the amount of necessary information that you would need to characterize the solutions. And then you use all that training data set to train a neural network. And the idea here is that the neural network is going to find some associations between the optimal values for the inverter functions and these input parameters that are simple features, kind of like the number of customers. So then if you have access to those features in a new feeder that is outside of the training data set, so you have a new feeder and, that feeder has 120 customers and 20% of them have PV, well, you can go to the neural network and predict this should be the coefficients for my inverter function that I should use. We implemented this in a set of like 126 real feeders from the UK. These were urban underground cable. And then we use some adopted topological features, kind of like total number of customers, the distance that there was between the distribution transformer and the last customer, etc. And then we trained the neural network. And the idea was that the neural network would be able to predict then what would be the values for a new feeder. And we tested them across different cases. So this is the result for a test feeder that was kind of like, was outside of the training data and was very representative of a very common type of feeder. And with a 60% of the customers having PBE, and we found that, well, the coefficients for the inverter function that would be predicted by the neural network would ensure that you wouldn't have any voltage violation, regardless of what your demand is, how the PBs are allocated on the system, etc. And to finalize, this is a current project that we're working on. It's called EV-Chip. This is in collaboration with the National Research Council from Italy. And the idea here is to propose some smart EV charging algorithm for campus-like facilities, such that the campus can work as an aggregator and not only, well, find a way of reducing the cost of charging the electric vehicles that are parked in the campus, but also provide services to the power system, kind of like reserve and ancillary services, like participating in the real-time pricing market. And the way we're implementing machine learning here is that one of the things that you would like to know if you're forecasting how should you be using the electric vehicles, how are you planning to charge them, you need information in terms of, well, when do you expect the vehicles to arrive? How long do you think that the vehicle is going to be there parking in the same place? What is the state of charge when the vehicle arrives? What do you think that the state of charge should be before the vehicle leaves, etc.? And what the people in Italy is doing with us is that they use a lot of images captured from like cameras in the different parking places, and using image recognition software, they were able to identify when every car was arriving to a parking place, how much time was it there, and then when was it leaving, and create like a data set of distributions of, well, this would be like the probabilities of the arrival times for the car into the parking place, how much time would the car stay once it arrives before it leaves. And using all this information, they use a supervised machine learning method in order to create a model that would be able to forecast how much, assuming that it's an electric vehicle, the electric vehicle would be plugged in. So if you know that information, you can perform some smart scheduling for the electric vehicle chargings, and then you can also have an idea of how much reserve you have if you want to provide reserve to the power system, or how much flexibility you have if you want to participate in the real-time market. So that would be it from my side, and I'm happy to respond to any question at the end. And if you want to contact me, that's my email. Thank you.
Thank you, Valentin, for another great presentation. I'll take back control here and I'll pass it over to Valerie. No, Valerie, I think.
Thanks, Keith.
No problem.
So as Keith said, my name is Valerie Lynch. I'm the data science manager for ESB. For those of you that don't know ESB, it's the utility industry and the main utility in Ireland. We have customers and employees across all of Ireland and the UK, and it operates completely across the electricity market, from generation, transmission to supply. So the use case that I'm going to look at today is a use case that was put into development with our customer supply business in Electric Ireland. But that doesn't mean that you can't use the same type of machine learning and classification for other areas across the industry. So similar use cases have been looked at for fraud detection, anomaly detection, document classification, and within generation, process planning, monitoring performance, as well as looking massive large data sets in order to be able to define and classify what information is in them. So huge variety of use cases, but for this particular one, I'm going to focus on our customer solutions side of the business and Electric Ireland specifically. Like I said, this is a use case that went into development a couple of years ago. And at the time, we were looking at about 1 million customers where it was a one-size-fits-all approach to how we collected aged debt with our customers. We had a serious lack of information and a lack of data to actually be able to understand what was happening with our customers, to understand what their preference was for how to collect the data and how we contacted them as well. At the time, like I said, we were taking a one-size-fits-all. It was a Dunning procedure that people got letters, they got SMSs, and they got phone calls. And it really didn't look at what the best use of our time and efficient collection agencies should be looking at. So we wanted to be able to categorize the customers based on their behaviors when in debt and prior to being in debt. We also wanted to make sure that it was the smallest amount of time because we are a highly regulated industry. So we have to make sure that our customers are paying us on time in order to meet some of our regulatory obligations. And then we had to use this information in order to be able to see, well, what's the best way of contacting our customers in order to recover this debt in the quickest way possible. And then proactively engaging with our customers to look at designing a contact strategy that would efficiently and effectively recover this debt with our customers. So the approach that we took, we looked at debt segmentation using clustering techniques, and we decided on a k-mean clustering algorithm quite early on in the journey to this. And it's really useful to be able to kind of group observations together with a lot of different variables and actually define how many types and groups of customers and behaviors within those groups through an iterative process. So the k-means, you basically have to refine your approach to specifying the number of clusters over a period of time. And we started off with a subset of data, which was about maybe 30,000 customers at the time. And we had to go through an approach of cleaning our data. This is something that is not mentioned in the machine learning world. It probably takes 60 to 70% of your time to clean your data, to get it into a good position so that you can actually start doing the fun stuff with all the machine learning and the classification afterwards. The way that we started the project was looking at the correlations of variables to our instance of likelihood to pay. And once we had our data set cleaned, we were able to actually correlate different variables based on this. We created new variables as well. So we had a total of 106 variables at the very end of this process, which was over about 30 million records for an 18-month period of time. And then we basically, because there were so many variables, we had to end up using heat maps in self-organizing maps specifically to characterize the customers in each of these instances. The variable creation, it was refined again as well. So we didn't end up with 106 variables feeding into our k-means model. What we ended up doing was looking at each of those, the correlation back to the customer likelihood to pay, and then decided that we would cut it down to about 20, 25 different variables that had a direct link to customers' indication to pay. And then at the very end, we ended up with 10 segments of customers, and defining these types and behaviors of the customers was really, really important because we had to explain that back to the business and applied that segmentation technique to the full customer base using the 25 variables that we had created and taken from our billing systems, as well as our customer contact systems as well. So you can see here that the self-organizing maps that we have here look at different variables, and the black outlines look at the groupings that we had defined. So customers that were highly correlated to each other and similar behaviors for that particular pattern. And then depending on the variable that we're using, you could actually see the types and behaviors and patterns of behaviors within each of those segments. So we were able to classify the behavior within these segments for each of these groups. So the overall result was really that we had two outstanding groups, that we had a pilot group and we had a control group. We were able to see a marked uptake on the pilot group against our control group of about 20 to 30% improved collections. The engagement was much more proactive from a business point of view, and it was based on the customer's needs and preferences. The design of that debt collection was with the customer segments at the heart of it. So looking at the patterns and the behaviors to be able to design that collection strategy. And then we ultimately had an improved timeframe to collecting that outstanding debt and overall debt issues, improving the debt collection and write-off performance that is KPI for the business. But as I said at the start, the other areas of use for this are huge. So we are looking at using it within anomaly detection, fraud detection right now within our business. And this is for both within the networks industry, looking at potential fraud on the network. Anomaly detection could be on wind turbines, looking at anomalies within the wind turbines themselves of performance and pattern behaviors. So it is probably a very light on the technical side compared to some of the other two use cases, but there is a vast array of different scenarios that you can use this segmentation and this clustering algorithms within the utility industry. So thanks, Keith. I'll hand it back to you.
Perfect. Thank you very much, Valerie, for another great presentation. Now we'll move into our Q&A session. Right now we'll do a Q&A session. So I'll be joined by Katie here, who will be asking the presenters any questions from the Slido if there arose.
Yeah, perfect. So might start with Rohit. So one of the first questions was, is a forecast produced through the ML models to more accurate the deterministic calculation on the PV production using historical solar radiation trends?
Yeah, it was. Thanks for this question. Yeah, it was. The data collected was from 2017 to 2018 and 2019. So for PV forecasting, I've used only irradiation at all the weather grid points, and the PV is the target variable for all these dependent features.
Okay, and then I think there was another question there. The ML models are trained from the solar radiation and PV powered production. Were there any other factors considered?
No, except irradiation, I have not considered any other factors.
Okay. I think we're just conscious of time, so I might move on to Valentine. One of the questions was in relation to smart metering. So they said ESB are currently rolling out smart meters across the country. Will you be able to incorporate the data from these smart meters into your data set?
I guess you could. I think that one of the most important things starting to have smart meters around there is that we're going to have more detailed information of what residential demand really is. So at the moment in which you're trying to predict in your model, like let's say, for instance, that you're working on the medium voltage network and you have a machine learning method which is forecasting what the demand is going to be, and you know that the composition of the demand is of certain percentage of residential, and you have more accurate data of what is the demand from residential sector, then you can perform a more appropriate scheduling of the resources that you may have in there. So yes. Then in terms of control at the low voltage system, you need to have more than just smart meters, because you need to have high resolution data, and that data has to be communicated with some controller in order to take action. So I think as of now, in terms of smart meter, it would be more of having more detailed information of customers' demand.
Okay, perfect. And I think we'll take one for Valerie. It was a joint question to Valentina and Valerie, but they said, is there scope for collaboration between ESB smart metering and debt collection?
Yeah, absolutely. I think that's the plan, is that debt collection would be reduced because of the accuracy of the smart meters and the meter reads that will be coming into the industry. So there should be a direct link in the reduction of debt with the increase of smart meters. So yeah, that would be great to see.
Yeah, definitely. And there's one more here for Valerie. Were there any challenges in gathering data sets on the customers to feed into the ML models because of GDPR?
Because this could be considered a service at the time as well that we were looking at it. We were finding that the classification was done on private information, so we wouldn't have had sensitive or identified customer information on the data set. So that wasn't a GDPR, I suppose, at the time wasn't a direct issue. When we did apply it to our customer base, then we did have to go through data protection impact assessments, making sure that our customers were aware that our data was being processed for this. If and when they do go into debt, that this is something that we do. It is within our terms and conditions as well that we process data for service necessary services, which this would be included under.
Okay. Keith, will I do one more question?
Yeah, we'll take one more question.
I suppose there's one for Valentine here. So they say, Valentine, you mentioned that these algorithms may be used to provide load shedding for EV charging. Do you think you can apply the same for electric heat pumps?
You can apply similar things. I don't know if you're familiarized with Nest or any of the smart home like energy management systems. At the end of the day, what they do is they grab information of what your demand is, and then they create at the end of the day a machine learning method that predicts what is going to be your house demand and your occupational patterns. So at the end of the day, if you can forecast when is people going to be home, when is people going to require for heating, then you can use the flexibility that you get from either electric smart heaters or heat pumps. And then, yeah, they make them work at the times that you actually require. And sorry, there's one question that I saw. There's just a quick comment on that. Someone said that what was the validity of the machine learning methods if you change the grid? So the thing with any machine learning method, if you're training it with a data set, as soon as the conditions of the actual system are very different from those of the training data set, the machine learning methods start being less accurate. So solutions to that are kind of like doing some dynamic retrofit of the machine learning method made based on new analysis of data or things like those. But generally, if you change the condition of the system from where you had trained the machine learning method, yeah, it starts being less accurate. Up to when is the point to retrain the method? Well, it depends.
That's perfect. Thanks very much, Valentine, for that. I think that's us finished. Now, just before we finish up, I just want to thank the presenters on behalf of the Engineering Group for their time in preparing their material and for presenting at the event this afternoon. I'd also like to thank the audience for their attendance at this event. It's encouraging to see a lot of interest in our events. And if you do like the content, please keep an eye out for further events this year. And again, thanks, Katie, for taking the Q&A session. And that's it for a wrap. We'll talk soon.
Thank you.
Yeah.
Thanks all. Great event. We got there eventually.
Yeah.
First time lucky.
That's it. Sure, look, it was a bit stressful there, but sure we got through it. I suppose we're always going to have possible technical issues. So Camille, well done again, and thanks all to all the presenters and everyone to help out. So yeah, thanks again, and hopefully we'll